Hi, now you can check out that EDC, electronic devices and circuits. So this EDC part is very important for particularly ECE stream. So it is one of the core subject for ECE stream in the GATE exam. So it can score good weightage in the GATE pattern, nearly around 10 to 12 marks it may going to be score. And as well as this EDC part can also help to the students who are preparing for PSUs, public sector unit conditions, and as well as research side like BARC, ISRO, DRDO. In different fields, this EDC part is very useful to the particularly ECE students. And not only that, so this EDC part, so considered to be have what means the semiconductor applications, that is nothing but diodes, BJT, FET, MOSFET. And I think that, MOSFET is nothing but most popular in VLSI designs you can call. So such as what means CMOS, complementary metal oxide semiconductor you can call. So nowadays, that electronics should be called as a microelectronics because the electronic gadget size comes to be very, very small you can call. Based on that, electronics now to be called as a microelectronics. That should be the application concept from the VLSI part. So let us now, we can discuss something about PN junction theory part now. Okay. So now I can able to examine something about PN junction theory. So let us see this one now. Semiconductors can be classified as two types, One is intrinsic, other one is what means extrinsic. Two types of semiconductors you may consider. One is what means intrinsic and extrinsic, This is the semiconductors. Appeared as what means two types. So one is what means intrinsic semiconductor, that itself called as a pure semiconductor also. So this is a semiconductor without adding any impurity you can call. So in the case of intrinsic semiconductor, right, the conductivity is very poor, so that it's not be preferred. So it can be added with some impurity you can call. Based on that, you may get the other body that to be what you can call means extrinsic semiconductor. So extrinsic semiconductor is a doped semiconductor or impure semiconductor you can call. So depending on the type of impurity you may add, so this extrinsic semiconductor classified as two types, One is N-type semiconductor. Other one is P-type semiconductor you can call. Right? How to get N-type semiconductor means it is obtained by adding a pentavalent impurity to a pure germanium or silicon of intrinsic you can call. The addition of a pentavalent impurity make one electron excess. So in this, electrons are the current carriers or majority carriers you can call. And who are the minority carriers in N-type semiconductor means, holes are the minority carriers. If you go for P-type semiconductor, there you are adding a trivalent impurity to a pure semiconductor. So the trivalent impurity make that holes to be excess you can call, right? Here, holes are the majority and electrons are the minority carriers. In the case of N-type semiconductor, the type of pentavalent impurity you are adding is nothing but what means arsenic, antimony, phosphorus, all these things. In the case of P-type semiconductor, we are adding the trivalent impurity such as what means gallium, indium, boron, all these things, right? So in N-type semiconductor, the current carriers are electrons, majority carriers. In P-type semiconductors, the majority carriers are what means holes you can call. And if I go for extrinsic semiconductor of N-type or P-type, what are the minority carriers you can call? Those are holes in N-type material and electrons in P-type material. How they can be considered means, so that minority carriers in N-type and P-type commonly considered by the breakage of covalent bonds with applied thermal energy. Such that in the case of semiconductors, the minority carrier concentration commonly considered with the breakage of covalent bonds by the applied thermal energy that commonly expressed as a function of temperature, And what is the applications of this extrinsic semiconductor means? So instead of using N-type and P-type material separately, commonly you are going to be combining an N-type semiconductor with a P-type semiconductor you can call. The resultant formation you may call as what means diode. So diode is obtained by diffusing P-type and N-type material together. So on diffusing P-type and N-type material together, you are getting what means a PN junction device. Okay. So what is that PN junction device? Now I can able to examine. So it is obtained by diffusing a N-type and a P-type material together, and the contact surface you can call as a junction. So this is the PN junction structure you can call. So how to diffuse P-type and N-type material means the diffusion of P-type and N-type material to be done not by any electrical joint or soldering, that to be done by what means taking a N-type of crystal, and over that you can keep a opposite of P-type crystal, and then you can able to heat that one to a high temperature so that one crystal can be diffused into the other. So I take one type of crystal of N-type or P-type, on that opposite crystal I can able to kept, and then I heat that one to a high temperature, then automatically you find that one crystal can be diffused over the other, and that contact surface to be called as a junction, you know, right? A junction is a contact surface between P-type and N-type materials, you can call like this. This would be called as a junction. Okay, so one side is a P-type material body, other one is what? N-type material body you can call. You know that in the case of P-type material, the current carriers or majority carriers are holes due to the addition of trivalent impurity. In N-type material, the majority carriers are nothing but electrons due to the addition of pentavalent impurity can call. If I diffuse P-type and N-type material together, what happen means, so across the junction, there should be some barrier effect you can call. Across the junction, there must be some barrier effect. So what is this barrier effect means? That barrier containing ions. That barrier containing what means? Ions. So this is the barrier that be considered across the junction of P and N sides. So on P side, you may find out negative ions. Those are called acceptor ions. On N side, you can find out positive ions, nothing but called donor ions. Okay. So once you can able to diffusing P-type and N-type together across the junction, there should be some barrier effect is there, right? This barrier containing only ions. It do not have any majority or minority carriers. It just have only ions. The type of ions are negative ions on P side and positive ions on N side. So this is the P side body. On the P side body, you know that the things that can be considered is what means holes, right? These are the holes. Here the current carriers are electrons, you know. So for every hole there is an associated negative ion is there. For every electron there is an associated positive charge or positive ion is there, right? It is a body of two terminal device, you know. Those are anode and cathode. This is anode, this is cathode. Remember now, this depletion region look like to be act as a dielectric body of a capacitor. This corresponding depletion region, what are the thing you can call? This depletion region act as a dielectric media of a capacitor, right? And once again, due to this corresponding PN junction body maintaining some internal junction capacitance. So this depletion region look like to act as a dielectric media, right, or insulating media of a capacitor, and whose edges, one is on P side, other one is on N side, they look like to act as a plates of the capacitor. By that, the diode body have some internal junction capacitance. Commonly you say that this internal capacitance is ignored at low frequency operation, and it is very, very effective if I go for high frequency applications. By that, you know, somewhat in our BZ amplifiers or FET or MOSFET amplifiers, you know that the gain come to fall off at high frequencies due to mainly internal capacitance. So not only in PN diode, it appeared in BZT, FET, MOSFET, all these things. And this would be effective only at high frequency and ignored at a low frequency operation, you can call, right? So remember now, it is an open circuit PN junction. I don't apply any external voltage. So here, due to this charges or due to this charge separation across this junction, you may find out some voltage. So I don't apply any external voltage there, right? So because of the charge separation by the depletion region, you must and should find out some voltage across the junction that to be called as a open circuit voltage or junction voltage you can call. So that open circuit voltage or junction voltage to be written like this, that is written as some V0C, open circuit voltage or junction voltage you can call Vz. So how much it is means, says for now, it is expressed by the thing like this, Vt ln of Nd Na by Ni square. So this is the expression for open circuit voltage or junction voltage there you can call. So what is that Vt? Where Vt stands for thermal voltage you can call. Vt stands for what means thermal voltage, you say that thermal voltage how much means 26 millivolt at room temperature. So Vt is a thermal voltage defined by Kt by Q, you can call, where K is a Boltzmann constant, T is the temperature, Q is the charge. So substituting K and Q, this is T by 11,600 volt, you can call. Right? At room temperature, it should be around means 26 millivolt. At room temperature of 300 degree Kelvin. So at room temperature of 300 degree Kelvin, it is around 26 millivolt, you can call. And I said that this should be what means thermal voltage. Right? That should be what you can call thermal voltage, What is this ND means? ND indicates the donor impurity density on N side. Added donor impurity density on N side. NE stands for added acceptor impurity density on P side, you can call. ND stands for added donor impurity density on N side. NE stands for acceptor impurity density on P side, you can call. And what is this Ni means? Ni stands for intrinsic carrier density, you can call, right? That represent the carrier density of the pure germanium or silicon you say, that is mainly depend on temperature, you can call. That is intrinsic carrier density, right? Ni stands for intrinsic carrier density of germanium or silicon by which the diode is made. Suppose under normal doping, what is this corresponding open circuit voltage means? It is around 0.3 volt for germanium diode and 0.6 or 0.7 volt for silicon diode, you can call. Okay, it should be around 0.3 volt for germanium body and 0.7 volt for silicon body. With that one, it can able to offer in some energy, right? Energy of the barrier, you can call like this. So this would be called energy of the barrier, EBI written. No? So how to write the energy means in terms of potential, I think that potential into charge, that is VOC into Q joules, right? So VOC stands for open circuit voltage or junction voltage, Q means a charge, right? That is called. And I think that 1.6 into 10 power minus 19 joules is nothing but electron volt, you can call. So same energy to be written in terms of electron volt like this, V0 C electron volt, where V0 C is nothing but the open circuit voltage or junction voltage, you can call. So based on that, how much it is means, it should be around 0.3 electron volt for germanium, okay, 0.7 electron volt for silicon. So this is the energy of the barrier. By that, it can able to oppose the carriers who try to move from one side to the other side, you can call. What are the carrier who try to move from one side to the other side can be opposed by this energy. So according to classical mechanics, any carrier who move across the junction from one side to the other side by having energy, that energy must be greater than or equal to the energy of the barrier, you can call. So that must be equal to what, sir, means the energy of the barrier. So how to provide that additional energy means that to be done by the applied bias. So the application of external source is nothing but what you can call, sir, means biasing, you can call. So you know that a diode can be biased in two ways, One is forward bias, other one is reverse bias. Without any applied bias, none of the carrier can move across the junction so that you don't get the conductivity. So to get the conductivity in a PN junction body, because of the barrier effect is there, you must should apply some source of energy. Application of source of energy to be called as a biasing, and the diode to be biased in two ways, One is what you can call forward bias, other one is what you can call reverse bias, you can call. And remember now here, this is the total width of the barrier, you say. This is the total width of the barrier. So what is the width of the barrier on P side means that I can call WP. What is the width of the barrier on N side means WN, you can call. Okay, width of the barrier is on P side I can call WP, and the width of the barrier on N side I can call what means WN, you can call. So total width of W equal to WP plus WN, you say. Let us see this one now. Whenever the barrier is formed, on P side you may find out loss of holes due to recombination. On N side you may find a loss of electrons due to recombination. Understood now? Whenever the barrier is going to be formed across the junction, under the preparation of the barrier, holes are getting loss on P side and electrons are getting loss on N side, you can call. Means there is some loss of positive charge on P side, there is some loss of negative charge on N side, you can call. But how much loss of positive charge on P side is equal to loss of negative charge on N side, you say. So based on that, you may examine what are the importance of the doping for barrier condition checkup. So this one small thing. So what I say, loss of positive charge on P side equal to loss of negative charge on N side, you can call. Loss of positive charge on P side equal to loss of negative charge on N side, you say. So let us see this one now here. Who is loss here? Holes are loss over a width of WP. I assume that junction area is nothing but what you can call, sir, means I can call. Already I told that NA stands for acceptor density. What is that acceptor density? Number of acceptor atoms added in unit volume, you can call. See this one now? Number of acceptor atoms added in unit volume, you say. NA stands for number of acceptor atoms added in unit volume. But the number of holes lost over the width of WP. In that width of WP, the volume is nothing but A into WP. So this is the number of holes that are lost on P side over width of WP, where A stands for junction area. So multiply with the charge like this. This represents the total loss of positive charge on P side over width of WP, where Na stands for acceptor density. Like that, you can go. Who loss here? Electrons are lost here over width of Wn, I told. So where Nd stands for donor density, you can call. Nd stands for what? Donor density, you can call. Right, a number of donor atoms added in unit volume, you say. So the number of electrons lost over width of Wn to be written like this now. So that is what means. You can write like this, Nd. So that represents the donor density, number of donor atoms per unit volume. So the pattern, electrons lost not over a complete one, or they lost only over a width of Wn, you can call, multiply with A into Wn, where A stands for junction area. This represents the total electrons lost over a width of Wn on N side, you can call, and multiply to charge. So Q cancel, A cancel. So what you find out means, there you observe now, Na into Wp equal to Nd into Wn. So this is the most useful condition in the case of PN junction part, where Na stands for acceptor density on P side, Wp stands for width of the barrier on P side, Nd stands for donor density on N side, Wn stands for width of the barrier on N side. So now we can able to rewrite this Wp by Wn equal to Nd by Na, you can call. Wp by Wn equal to Nd by Na. So from this you observe now, width of the barrier on P side inversely proportional to doping. Width of the barrier on N side is inversely proportional to doping. So in the case of PN junction body, you remember that width of the barrier, right, either in P side or N side, like this, width of barrier always inversely proportional to doping. Okay. Higher the doping, lower the effect of the barrier. Lower the doping, higher the effect of the barrier, you can call. Lower the doping, higher the effect of the barrier. Higher the doping, lower the effect of the barrier, you can say. So width of the barrier always inversely proportional to the doping order. Confirm my option. So depending on the doping profile, the PN junctions are classified into two types. One is what means, one of that one is linear graded PN junction, other one is nothing but a non-linear or step graded PN junction, you can call. Depending on the doping profile, one is what you can call means linear graded PN junction, you can call. Linear graded doped PN junction. So this is one of that, right, where you remember that what are the doping order on P side and N side should be same. That is what you can call means doping condition of N and P side same means Nd equal to Na. So what are the doping order and N side should be same as the doping order on P side, you can call. So automatically what you can find out means the width of the barrier of P and N side should be same. What are the width of the barrier and N side? should be same as the width of the barrier on P side. Right? This is one of the case. Other one is what means. One more is what means non-linear or step graded PN junction you can call. Non-linear or step graded PN junction you say. In this, the doping order is different on N and P sides you can call. Right? So it to be appeared as what means like this. It to be appeared as what you say means P plus N or Pn plus you can call. So what are the superscript plus indicate that as compared to the other side, this one is a highly doped one. So here P side is highly doped than compared to N side. Here N side is highly doped than compared to P side you can call. So that to be called nonlinear or step graded PN junction you say. Suppose for P plus N junction you say, for P plus N junction if I go, so doping order on P side should be greater than doping order on N side. Na greater than Nd. Then what the meaning of this one means? Just now you know that width of the barrier is inversely proportional to doping. So based on that, what are the width of the barrier of P side is negligible than compared to N side. Width of the barrier on P side is negligible than compared to N side you can call. Right? Suppose if I go for what means, okay, if I go for, so if I go for Pn plus junction, if I go for Pn plus junction, what you can able to find out means the doping order of N side should be greater than P side you can call. That is Nd greater than Na. Nd greater than what you can call, sir, means Na you can call. Nd should be greater than Na you can call. So Nd greater than Na means automatically Wn less than Wp. Okay, width of the barrier on N side should be less than the width of the barrier on P side you can call. Width of the barrier of N side should be less than width of the barrier on P side you say. Understand now? So there are two types of PN junction based on the doping profile you can call. One is a linear, other one is a non-linear you can call. In the case of linear, the doping order on N and P side should be same, equally doped one, so that the barrier effect is equal on both the P and N sides. If you go for non-linear or step graded PN junction, you know that one is more doped than compared to the other one. So based on that, the width of the barrier to be like this. Suppose if you go for BZT, there emitter is highly doped than compared to base. So whenever you can define the barrier, that barrier is mostly expanded into the base, never into the emitter you can call. So in that format you can able to examine, right? And now you see this one again. So total width of W equal to what do you know? Wp plus Wn you can call. Total width of W equal to Wp plus Wn you say. Now that can be expressed like this you say. Total width, now I can able to go for like this. See this one. Total width of W equal to Wp plus Wn you can call. Okay. And you know that Wp becomes W minus Wn, right? Now, one of the relation you know already. Na into Wp equal to Nd into Wn, you know. Right, Nd into Wn you can call. Now, what will I do means, I substitute this Wp value here. Na into Wp is what means W minus Wn you can call. That equal to Nd into Wn, right? Now, I want that Wn there. So now I can able to rewrite like this. Na into W, take Wn common there, it becomes Nd plus Na. Right? It becomes as what means Nd plus Na you can call. Then Wn becomes what means like this. Wn equal to Na into W by Nd plus Na. Okay, the width of the barrier on n side equal to total width into opposite density by sum of the individual densities you can call. Similarly, if you go, okay, also WP if I write, what you may get, that become as ND into W divided by ND plus NA. Understand now this doping conditions? Width of the barrier on N side, width of the barrier on P side you can call. And you discuss that right, without applied bias, no conductivity in the case of a diode. So how many ways of biasing means? Two types of biasing you know. One is what you know, sir, forward bias. Other one is what? Reverse bias. How do you say the diode is in forward bias means? So diode look like be in forward bias if the anode voltage made positive with respect to cathode. Confirm my option. One of the biasing I said simply. One of that one is a forward bias I can call. When do you call the diode is in forward bias means? So anode is kept at positive potential with respect to cathode you can call. Anode is kept at positive potential with respect to cathode, then the diode look like be in forward bias. So this is the symbol for a diode using. So diode is a unidirectional device because it allows the current in only one direction, that is from anode to cathode. Commonly can use the symbol of the diode to be like this. So that indicate a unidirectional device. Based on that, the diode can act as a switching element, and with that switching application, it can be used as a rectifier. Okay. So forward bias means anode is kept at a positive potential with respect to cathode, like this. So this is the indication of it. So in this forward bias mode, it can allow the current. So it is a body that can allow the current in this forward bias mode. By that, the diode in forward bias can act as a closed switch. Okay. In this forward bias mode, the diode can allow the current, and thereby it can look like they act as a closed switch. And practically if we go, so the majority carriers can able to move across the junction and recombine each other, and thereby they can able to cause the current conductivity in forward bias. None of the minority carrier can move across the junction there. Who to be move across the junction in forward bias means only majority carriers can move across the junction, and that can recombine to generate the current. And this should be happen only whenever the applied voltage should be above the barrier potential, not below the barrier potential you can call. So in the forward bias, the conductivity of current possible once the applied voltage cross the barrier potential you can call due to the recombination of majority carriers across the junction you say. And practically you remember now, this current conductivity in forward bias is exponential. Means for a small change in voltage, there is a rapid growth of current in forward bias. And commonly you say that in forward bias, the current is strongly dependent on applied forward bias voltage. This is the case in forward bias simply. One more you know, that is reverse bias. In the case of reverse bias, what you say means the anode voltage so is at a negative potential. The anode is at a negative potential. Anode is maintained at a negative potential with respect to cathode you can call. Here anode is maintained at a positive potential with respect to cathode. Here anode is maintained at a negative potential with respect to cathode I told. In the case of forward bias, anode is at a positive potential with respect to cathode you learn. But in the case of reverse bias, A to Z is opposite there. So here the anode is at a negative potential with respect to cathode like this. This is anode, you know. This is cathode. So the condition is a reverse mode here. This is the case. Anode is maintained at a negative potential with respect to cathode. Right. So remember that in this mode, none of the majority carrier can move across the junction. Instead of moving across the junction, the minority carriers can move away from the junction. Thereby, in the case of reverse bias, the barrier effect can get widened such that there is no chance for the diffusion and recombination of majority carriers. There can expect the current by minority carriers. And this minority carrier recombination is very less value here, such that a diode in reverse bias can able to act as an open switch. That minority current commonly called as a reverse saturation current I0 or IS you can call. And that current is strongly dependent on what means temperature. So that minority current strongly depend on what means temperature, which is about microampere for germanium and nanoampere for silicon. Ideally no current flows, practically only minority current flows you can call. That anyhow negligible about microampere or nanoampere you can call. Microampere in the case of germanium, nanoampere in the case of silicon. So in reverse bias, the current mainly due to recombination of minority carriers, that strongly depend on temperature, not on voltage. By that, the current in reverse bias to be called what, sir, means reverse saturation current you can call. Reverse saturation current you say. That will be denoted by what means I0 or IS. So practically to remember that this minority current can almost doubles for every 10 degrees centigrade increase in temperature you can call. This minority current can almost doubles for every 10 degrees centigrade increase in temperature. Let us see this one now. Suppose you say that I01 is the minority current of the PN junction under reverse bias at a temperature of T1 degree centigrade. For the same body, I02 is the minority current at another temperature of T2 degree centigrade, keeping reverse bias voltage is constant. Keeping reverse bias voltage is constant. Then what is the relation between this one means I02 equal to I01 into 2 power of T2 minus T1 by 10 ampere. So this is the relation for that. So minority current get doubled for every 10 degree centigrade increase in temperature you can call. Anyhow, it doubles or triples, it's not the case. The minority current is too less you can call, such that the diode in reverse bias commonly considered as a open switch. In forward bias, the current due to majority carriers. In reverse bias, the current due to minority carriers. In forward bias, the barrier effect comes to sub-compressed you can call. Here the barrier effect comes to expanding you can call. Here the current increasing rapidly with the forward bias voltage, such that current mainly depend on voltage. Here current mainly depend on temperature you can call and independent of voltage. So what are the VI characteristics of a diode for both forward and reverse means that VI characteristic may come like this. So this is the VI characteristic body, VI characteristic of a diode. See this one now. So this is the VA characteristic of a diode you can call. So if I go for the VA characteristic of a PN diode, that may come like this. So this is plus V. Plus indicate forward bias option. Minus V for reverse bias. Polarity of V is positive for forward bias. Negative for reverse bias you can call. So this is the current you can call. Forward current. Commonly it should be order of milliamps. This is a reverse bias current you can call. Order of micro or nanoamps. Okay. So now can able to examine. So what is the characteristic graph for that? Suppose if I go for forward bias, I told that up to certain voltage the current is negligible. That is due to barrier effect you can call. So that barrier effect is nothing but defined by VR. That is also called as a cut-in voltage. So it is about 0.3 volt for germanium, 0.7 volt for silicon, you know. That is due to the barrier effect you can call, right? Cut-in voltage you can call. Once you can able to cross this one now, for a small change in voltage, the current increasing rapidly, such that the diode commonly considered as what means non-linear device, because for a small change in voltage, the growth of current is exponential. The diode commonly in forward bias can able to act as a what means closer switch there, and the growth of current is exponential means the diode commonly called as what means a non-linear body. So this is the place where the diode can act as a on switch. Got it? You know that in the reverse bias, the current is mainly due to minority carriers, and that current is negligible, you know, so that that current may come like this. So this current mostly due to temperature, and it is independent of voltage. So even this current flows that is a negligible one, diode in reverse bias can act as a open switch you can call. So this is the complete area of off switch. So diode not only off switch in reverse bias, it to be off till the breakover voltage or cut-in voltage you reach of forward bias. So commonly you remember now, this cut-in voltage look like as a internal reverse bias of the diode you can call. It look like as a internal reverse bias. Once you can cross this one now, the diode can able to conduct. So from this VI characteristic graph, you remember now, diode have a slow switching response due to barrier effect you can call. Once the barrier effect can be neglected, the switching response can be improved you can say. So this is the reverse bias condition. So this is the VA characteristic of a PN diode you can call. So now I can able to check out what is the equation of current concept from the Shockley. See this one. So this is a Shockley equation for a diode. So it can also be applicable for a BJT body. So Shockley equation of current for a diode you can call. So that to be expressed as like this. The current in a diode I equal to I naught into exponential of V by eta Vt minus 1 ampere you can call. So this is the standard equation of current for a PN diode using Shockley, where I stands for current in a diode, V is the applied bias voltage that I taken for positive for forward bias, negative for reverse bias. Already you know I naught, minority current, reverse saturation current, strongly dependent on temperature. Vt you know, thermal voltage, right, that is kT by Q I told, and at room temperature it is about 26 millivolt you know, right. So for forward bias V is taken as a positive. And here you remember this. What is this? Eta means, eta considered to be what means ideality factor you can call. Eta to be considered as what sir means the ideality factor you can say. So eta should be same as what sir means ideality factor. So where eta stands for what means ideality factor, that I write go for now. Eta equal to ideality factor you can call. Sometimes it is also called as a recombination factor. That to be value is nothing but 1 or 2 you can say. How it can be taken means the junction body of high conductivity taken as 1 and for a junction body of less conductivity taken as a 2. Probably for germanium body it is, for germanium PN junction it is 1, for silicon PN junction it is a 2 you can call, right. Eta equal to 1 or 2, that is the ideality factor use. Vt is the thermal voltage use. V stands for applied bias voltage. Suppose for forward bias if I go for forward bias, V to be taken positive, that is applied bias voltage. Then what is the approximate equation of current in forward bias means V taken positive means exponential of this factor to be high, automatically 1 is neglected. So current in forward bias to be like this. Now I can write some IF, that is current in forward bias use. It is nothing but like this, I naught into exponential of V by eta Vt ampere. So that should be the current in forward bias you can call. Suppose if I go for reverse bias case, what happen, right? So in the case of reverse bias, you take V equal to negative. You take V equal to negative, then so if I take V equal to negative, this becomes as a 1 by exponential now. So exponential value greater than 1 means 1 by exponential value negligible as compared to 1. So at that condition, this exponential factor come to vanished, so that it becomes what means I equal to minus I naught there. Okay, V equal to negative. Then current in reverse bias, now I can call some IR, that is approximately equal to what means minus I naught, where negative sign stands for what means reverse bias case you can call. Negative sign is the sign for what's a reverse bias condition you say. And so now if I take V negative there, this exponential 1 by exponential value it comes, that to be neglected as compared to 1 you say, so that current in reverse bias is close to what means minus I naught. So in reverse bias you remember that current is independent of voltage. It depends on I naught. I naught strongly depend on temperature you can call. And the negative sign stands for what's a reverse bias.